Dear learner, I am Dr. Rupam Sankarnath, Assistant Professor, Discipline of Mathematics, KK Hendik State Open University. Welcome to the Module 9 of the Open Source Software for Academia, and this is Lecture 25, Application of Scilab 2. In this lecture, we will learn the key features of Scilab for numerical analysis, and we will learn the numerical Newton-Raphson method and bisection method. Also, we will see some numerical integration method like trapezoidal rule, Simpson's 1/3 rule, and we will see how to solve some linear system of linear equations by direct method like Gauss elimination, how to implement the programs in Scilab, and we will also see the iterative method like Jacobi and Gauss seidel method. Numerical analysis. Numerical analysis is a branch of mathematics that deals with some algorithm for solving high-level mathematical problems numerically, and it is an open software, and we can easily solve those problems, numerical problems in Scilab easily. Which are already widely used in physics, engineering, data sciences, and other scientific fields. The key feature for numerical analysis: it is a built-in software. Scilab widely used in numerical integration, differentiation, optimization, and solving equations, and many more other things. Ease of use. We can easily use Scilab, and we can easily learn and how to solve the problems in Scilab. And visualization. Scilab can easily generate plots and graphs for data analysis and is visualized. Cost effectiveness. Scilab is an open free software, and it is the alternative for MATLAB, which is a very expensive software. Analysis in Scilab. Here we can solve nonlinear equations in Scilab. The problem: find the roots of nonlinear equations f of x equal to 0. Newton-Raphson method. The steps to implement this method: step 1, define the function f of x. Then we have to define its derivative. Then choose a initial guess for the root, and like x not equal to 0, something like that. And then use this formula x and this formula, and this is the derivative of the function f, and repeat this until the desired accuracy is achieved. This is the program of the Newton-Raphson method in Scilab. Here first we have to define the function f of x. Then next we have to find the derivative of the function and define this function derivative, and then we have to choose an initial guess for the function. For this problem we have chosen the initial guess is equal to 2, and the tolerance is this, same as the 6 digit, and maximum iteration we have taken as 100, and this is the main program for Newton-Raphson. If the derivative, the function is 0, then we have to avoid the function, so we have implemented this. If this is 0, then we cannot use this formula, then it shows that derivative is 0, stopping iteration. And if it is not 0, then use this formula x1 equal to x naught f of x, and this is d of dx, and repeat this until the desired accuracy is achieved. For this part is checking for convergence, and finally we get the answer. Let's implement this in Scilab, and this is the result. This is the form. We have defined these functions, and this is the initial guess. If we implement this in Scilab, we get the result, and the converge to the root is 2.690. This is the convergence root. We can implement the Newton-Raphson method in Scilab like that. Next, bisection method. The bisection method is a numerical technique to find a root of a function f of x equal to 0 within a given interval a b, where f of a and f of b have opposite signs. Then you can use this method. And steps to implement this method: verify the roots exist within a comma b by checking f of a dot f of b is less than 0, and then we have to calculate the midpoint of both the intervals, which is a plus b divided by 2. Then check the sign of f of c. If f of a into f of c is less than 0, then set the b equal to c. If f of c dot f of b is less than 0, then set a equal to c. Repeat this until desired accuracy is achieved. Let's implement this in Scilab. First we have to define the function f of x, and this is the main function. Then we have to input the interval a comma b. Here a is 1 and b is 2. Then we have to find the desired accuracy, which is the we term as a tolerance, and we also take maximum iteration is 100. First we have to check the roots, if the roots exist between the interval. If f of a into f of b is greater than 0, then it shows that f of a must have opposite signs, and quit. We implement this thing. We want that f of a dot f of b should be less than 0, not greater than 0, so we use this function. And then the bisection method starts from here. K equal to 1 to maximum iterations, and c is midpoint a plus b, and then f of c becomes f of c. And this is the stopping criteria. If tolerance, we get the answer desired root is less than tolerance, then it shows the root. If it is not, then f of a into f of c is less than 0, then b equal to c. This is that thing we have written in the Scilab, and these are the answers. This is the main program. MCQ 1. In bisection method, what is the main requirement for the function f of x in the interval f a comma b? F of a and f of b must be equal. F of a and f of b must have opposite signs. F of a and f of b must be non-negative. The derivative of fx must be 0 in the interval. And the correct answer is f of a and f of b must have opposite signs. Then numerical integration. In numerical integration, we have compute the integration from a to b f of dx function by using trapezoidal rule. Trapezoidal rule formula is like that, where h equal to b minus a divided by n, the width of the sub intervals. This is the formula, and this is the program of the trapezoidal rule. Here we have defined the function to integrate, and the a equal to 0 is the lower limit of the integration, and b equal to 2 is the upper limit of the integration, and here n means the number of sub intervals, and step size h is b minus a divided by n. Then we have to compute the by trapezoidal rule f of a plus b, and this is the thing, and this is the result, and then we get the displayed. The result is this. Let's implement this in Scilab. Let's implement this. If we run this program, then we get the approximate integral using the trapezoidal rule. This is the answer, and here we have already defined that this is the main function, this is the lower limit, upper limit, and this is number of iterations and step size, and this is the main program formula of the trapezoidal rule, and this is the final result, and we can display the result is something like that. This is the main program. Next, there is another method, Simpson's 1/3 rule. For integral, we can also integrate from a to b by using Simpson's rule for n sub intervals. This is the formula for Simpson's 1/3 rule, which is different from the trapezoidal rule. By improvising the formula, we can get the more accurate root in Simpson's 1/3 rule. And this is the program for Simpson's 1/3 rule. Similarly, like trapezoidal rule, we have to first define the function here, and then we have to put the lower limit of the integration, then upper limit, then number of sub intervals, and the number of sub intervals must be even for trapezoidal Simpson's 1/3 rule, and we have to check that n is even or not. If it is even, then we can display this. If it is not even, then this program runs, and if it is even, then go to next process. And this is the step size, and this is Simpson's 1/3 rule formula. This thing is this formula for 2 or for I equal to odd, this part is necessary, and for I equal to even, this part is required. Then this is the main thing, and then we get the desired results here. Then we have to implement this in Scilab. Copy the program and paste it here. Then we get the desired result for Simpson's 1/3 rule. This is the root, and we have similarly like trapezoidal rule. This rule, Simpson's 1/3 rule, is implemented here, which is I have already discussed in this program. Next, MCQ 2. What does the trapezoidal rule in numerical integration approximate? The area under a curve as a sum of parabolic segments. B. Option B. The area under a curve as a sum of trapezoidal segments. The solution of a linear system. The eigenvalues of the matrix. The answer B is the area under curve as a sum of trapezoidal segments. Here we can also solve linear equations, which I have already discussed in the previous video. In Scilab, something the matrix, we can solve the matrix by using the backlash operator, and also this is the direct method. And in iterative method, Jacobi and Gauss seidel methods can be implemented, which will be discussed after few minutes. And we can also interpolate and curve fitting in Scilab. This is the code for Scilab. Next, Gauss elimination. Steps of Gauss elimination. Let us consider n linear equations with n unknown represented in matrix form as A, x equal to b, where A is the coefficient matrix and x is the vector of unknowns and b is the right hand side vector. First we have to find the augmented matrix. Combine the coefficient matrix A and result vector b to form a augmented matrix A/b. Then by using forward elimination, we have to perform some row operations to convert the augmented matrix into a upper triangular form. Then by step 3, by using the back substitution, solve the unknowns starting from the last equation to the first equation. Then we get all the values of the equations, and this is the Gauss elimination. For example, this is a equation. These are some equations, 3 equations are there. Then we have to first step 1, we have to convert these equations into augmented matrix. This is the main matrix A, and this is the right hand side vector. And step 2, by using the forward elimination, we have to convert the matrix into upper triangular form. Then we have to take the first pivot A11 equal to 2, because this is the first element. We have to convert the matrix in upper triangular, so we make this row 3 and column 3 first element become 0. Then next pivot is A22 equal to 0.5, and this is the upper triangular matrix. We have already converted this, and by next step 3, we have to solve this equation by back substitution. from last row we get that z equal to -1. This is z, this is for x, this is for y, and this is x. Then from the second row we get 0.5 y plus 0.5 into z equal to 1, and we have already get the value of z equal to -1, so we have put this value z equal to -1 in this equation. Then we get the value of y equal to 2. Then we have already get z and y value. Then from the first equation, 2y6 plus y minus z equal to 8, and we have put this the value of z and y here, and then we get x equal to 3, and this is the solution: x equal to 3, y equal to 2, and z equal to 1. Now we have to implement this in Scilab. This is first step. We have to define the coefficient matrix and augmented matrix. This is the coefficient matrix, and b is the right hand side vector, which is a column vector, and a is the matrix, main matrix. Then we have defined the augmented matrix as a comma b, and we can display the augmented matrix something like that. Then step 2, we have performed the forward elimination by using this. Then we can eliminate the pivot element in the second column, and we get the upper triangular matrix. We can also display the upper triangular matrix. Then step 3, we have to perform back substitution by manually solving for z, y, and x for upper triangular matrices. First we have to solve for z, then we have to solve for y, then we get the value of x, and then we can get the value of the solution and display the solutions here in Scilab. We can also verify the solution with a built-in solver, a backslash method. That this method is the Gauss elimination method. Answers are correct. Now implement this in Scilab. This is the A coefficient matrix A, and this is the augmented matrix. Here these three first three columns are the matrix A, represent matrix A, and the right hand side of the vector represent matrix B, a right hand side vector. This is the augmented matrix. Then we have to perform the forward elimination. Let's copy this file and perform the forward elimination. We have already performed, and we get the upper triangular matrix after performing the forward elimination. Then we have to use the back substitution method, and we get the value of z, y, and x. If we perform the back substitution, then we get the value of z first, then y, and then x, and z equal to -1, y equal to 3, and x equal to 2. Let's get the solution by using the backslash method and compare the solution with the Gauss elimination, and we get that x equal to 2, which is the correct, y equal to 3, and z equal to -1. Both the solution are same, so the Gauss elimination method is program of the Gauss elimination method is correct. We can implement this like that. First we have to define this coefficient matrix and right hand side vector, and we get the augmented matrix. Then we have to perform the Gauss elimination by using forward elimination. Then we get the upper triangular matrix after that, and after that we have to perform the backward substitution, and we get the value of x, y, z. We can verify our solution by using the backslash method. Then the next method is Jacobi's method. The key concept of Jacobi's method: first we have to decompose the matrix A into D plus R, where D is the diagonal elements of the matrix A and I is the remainder of diagonal elements. then we have to use the iterative formula. This is the iterative formula, and here x to the power k plus 1 is the solution vector at the k plus 1 iteration, and x to the power k is the solution vector at the kth iteration. Convergence criteria: the method converges if A matrix A is diagonally dominant or symmetric positive definite. The iteration stops when this criteria fulfills, and here is the tolerance. And this is the Jacobi's matrix equations. For we have to define the coefficient matrix similarly like Gauss elimination. First we have to define the matrix coefficient matrix A, then the right hand side vector, and here we have to initially we have to define the initial guess, and here our initial guess is 0, 0, 0, and the tolerance is this, and we have considered a maximum iteration should be 100. Then we have to decompose this matrix into diagonal matrix and the remainder. Let's copy this code, and then we have to perform the iterative Jacobi's formula, and then we get these outputs. Let's implement this in Scilab. Let's copy this code. Matrix D and R, we have to find the matrix D and R. We have already get here D and the matrix diagonal matrix D, and this is the diagonal matrix, and this is the remainder matrix, and then we have to perform the iterative Jacobi's method. Let's run this file. Then we get the solution of the above equation, which is x value is 1 point something like that, and y is 2.06, and z is this, and the maximum number of iteration is 20 here. And we can implement this Jacobi's method some here like that. Next, Gauss schedule method. The key concept of Gauss schedule method, and the iterative formula for Gauss schedule method is this, where xi k to the plus 1 is updated value for I variable at the kth iteration, and a double I is diagonal elements of the matrix A. The updated values are immediately used in the current iterations, and this is the convergence criteria for Gauss schedule method. This is the example. These are some equations, and this is the A matrix we can call it, and this the 6, 25, this is the right hand side vector. And steps 1, define the coefficient and initial guess. Gauss schedule method in Scilab we have defined the A matrix coefficient matrix, this side equations 10 minus 1 2, and the fourth x4 coefficient is 0, so 0. This is the coefficient matrix A, and this is the right hand side vector B, 6, 25, minus 11 and 15. Initialization n is size number of equation, and this is x means initial guess, and the conversion criteria, and this is the maximum number of iterations. Next, this is the main iterative formula for Gauss schedule method. This is the main program where Gauss schedule iteration is k equal to from 1 to maximum iterations. Save the previous iteration values k whole equal to x, and this is the loop for I to 1 to n, some unknown terms, and updated here, and then we computed the sums here, and then the current values, updated the current values, and then we have to check for convergence. If the convergence is less than tolerance, then we get the answer and number of iterations. If it is k equal to maximum iterations, then warning, maximum numbers on iteration is reached without convergence. Now let's implement this in Scilab. We have pasted the first the matrix and the initialization right hand side vector and the number of equations and initial guess, then maximum number of iterations. then we get the solution x equal to 1, x1 equal to 1, x2 equal to 2, and x3 is minus 1, and x4 is 1, and thus it converges after 8 iterations. This is the program, and we get the solutions here. Like previously, we have also implemented the Gauss elimination and Jacobi method. Now this is the output, same as the we get, and converges after 11 iterations. MCQ 3. What is the primary difference between Jacobi and Gauss schedule method? Option A, Jacobi uses updated the values immediately, while Gauss schedule uses the old values, and Gauss schedule updated the values immediately, while Jacobi uses the old values. And option C, both uses updated values immediately, and option D, both use only old values. The correct option is option B, Gauss schedule uses updated values immediately, while Jacobi uses only the old values. MCQ 4. What does the Gauss elimination transformation of a system of equation into? A diagonal dominant matrix, a lower triangular matrix, an upper triangular matrix, and a sparse matrix. And the correct answer is an upper triangular matrix. We have also seen this in Gauss elimination, that we get the upper triangular matrix by using the forward elimination, then by using the backward substitution we get the solution of the matrix there. Here we will see the summary of the lecture 25. In this lecture we will already learn the Newton-Raphson's method and the bisection method, how to implement those methods in Scilab. We will already learn the trapezoidal rule, Simpson's 1/3 rule, and how to implement those algorithms in MATLAB, and how to get the convergence criteria, how to get the roots and easily, and which are the fastest method. Overall, Scilab is a powerful tool for performing numerical computations. At the end, we can know that all the problems of numerical analysis we can solve it in Scilab very easily as compared to the MATLAB. This is the end of lecture 25. Thank you.